Hello, everybody. I'm Mike. I'm going to present our attempt to implement Zerocopy receive for virtual host, which didn't succeed much. Most of the work was done by Kalman Math, who's listed first here, but he couldn't arrive, so I volunteered to come to Edinburgh to taste whiskey. So here we are. As all of you here probably know, there is some trade-off between flexibility or configurability and performance, where you go from bare metal to through IOV to paravirtual device, and finally E1000 is probably the most flexible, but I believe nobody is using it anymore. So what we hope to achieve with Zerocopy RX is to make paravirtual device a little bit closer from the performance point of view, but still make it flexible and configurable. Unfortunately, what we got was something like that. The motivation behind the whole project was obviously, if you copy something, you can skip copying. It's better. Since TX is already implemented, probably we can do RX to make the picture symmetric and complete. And to be more serious, when you run perf on a vhost process, you see that 46% of the time with a large packet traffic is coming from copied user generic string, which is quite a bottleneck. And we hoped to resolve it. Now, TX was implemented quite a while ago, and RX is still not there because there are some differences that make TX receive a little bit harder than transmit. With transmit, the data is at hand, and you can just say your hardware device driver, here's my data, please send it to the network. And when you're done, unpin the pages. For the RX part, the device has to know in advance where to put the arriving data so that it will be seen immediately by the guest without the need to copy. We had several assumptions in our implementations. First of all, all modern NICs are multi-queue, so we can dedicate one or more physical queues to virtual queues. We checked different alternatives for who will be responsible for actual memory allocation. And one of the ways it's possible to allocate memory in the device driver and then remap it back to the guest. But this option seems to be much more complex than make the guest allocate the memory and then pass it down to the device. Since Zerocopy RX requires tight coupling between physical and virtual queues, we decided to restrict our implementation to Mach VTAP only. And our goal was to minimize changes to the guest, and if it would be possible, avoid them at all. It didn't work out. Though. I can point with it, right? Somehow. OK, so the packet goes like that. It passes on the way MacVil and MacVTAP and Virtio, and ends up in the guest kernel buffers for Virtio device driver. What should have been a nice feature is that hardware directly places the data into the rings that is shared between the guest. That is shared between the guest and the physical adapter. We did a couple of changes in our implementation. First, to the generic netdev struct, we have added 2 methods to support, first of all, initialization of memory and say the device is going to be Zerocopying, that it would move data directly to the guest. And then we added method that allows Rx part of a device driver to notify upper layers in the stack that data is arrived and it should be taken care of. At the Mac VTAP, we've added also two messages that used in communications between vhost and Mac VTAP. One of the messages notifies Mac VTAP there are new buffers that guest has allocated, and these buffers should go downstream to the device driver, so it will use it in its receive ring. And the second message indicates that there are buffers that should propagate to user space, and their pages can be free, more or less. We had to change virtio-net a little bit. We wanted to save effort and cycles on translating virtio descriptors to page and vice versa. So we added a new allocation method that allocates an entire page for a single virtio descriptor. When the system is initialized, we isolate a set of queues in physical NIC. In our particular implementation, we used L2 offloading of a XGB driver. And at the same time, there is a bonding between the physical RX queues with virtual RX queues. The physical RX descriptoring is cleared, and the pages that were allocated by the device driver from the host memory are cleared as well. Whenever guest allocates memory for virtio-net on behalf of virtio-net, vhost is notified, and in turn it notifies a Mac VTAP, and Mac VTAP allocates an SKB for the newly allocated memory and fills SKB with appropriate pointers to the fragment. And using the new method we introduced in netdev, it posts the buffers downstream to the device driver, which in turn creates appropriate hardware descriptors in its RX ring, so that whenever there is DMA of the incoming data, it will go directly to the memory visible by the guest. Then whenever there is a receive, the packet data DMA directly to buffers visible by the guest. There is a new SKB that is, the SKB that was created previously in Mac VTAP is adjusted to properly point to the right data, and its header are updated. And then physical device driver calls native RX. It transfers the control to Mac VTAP. Mac VTAP queues the SKB as ready for user space and notifies vhost.net. At vhost.net, there's some manipulation between page data and virtio descriptors and some level of translation. And after the translation is done and virtio descriptors are ready, Mac VTAP is notified again, and it performs the final cleanup because SKB is not needed anymore, and the guest already sees all the packet data as it arrived. So we've reached to a point where the implementation was stable enough to run netperf. It still was suboptimal from my perspective. There are some changes to implement, but we find out that despite minor optimizations we could do, there are some more major problems we were facing. And at that point, the European project that sponsored the whole project has ended. We've run out of funding, and it's via research. We need to have, well, you know how it works. So for anybody who's interested, the prototype is available at these repositories. One is for kernel, is based on 4.8. And one is for QEMU with minimal changes to allow negotiation of Zerocopy RX feature available in vhost from one side and for virtio on the other side. Now, a little bit what we tested and what we were able to find out and why we think we couldn't do improvements with what we proposed. So we had two server systems back-to-back connected with 10 gigabit Intel NICs. VMs VM was running with 4 vCPUs, 2 gigabyte RAM, and one of the system we were running NetPerf server, the other one was NetPerf client. The NetPerf client was run on bare metal, which was talking directly to Mac VTAP connected to the VM. So after we've run the benchmarks and we've seen that we're getting lower rates but still high CPU utilization, we checked what perf is going to tell us. And we've seen that copy to user actually has gone. And there is no clear bottleneck as it was previously. And apparently everything should be good. But it wasn't. So we've started to investigate where is the CPU time spent and when we can process data at least as fast as baseline. So first thing we tried is to create some CPU affinity between vhost and the interrupts of the device. And what we've seen that this improves the situation, and with CPU affinity, when we were forcing vhost to run on a different processor than on different cores than RX interrupts, we got much better performance than previously. We still used more CPU than the baseline, and we were not too happy about that. So perf again, what we were able to find that bottleneck now moved from copy datagram to Intel map page. What is happening is that in normal operation, a NIC device driver maintains a page pool and it recycles the pages whenever it runs out of memory. And when it does the page recycling, it also updates all the DMA maps. For every page it allocates, it calls DMA map at the time when it allocates the page. Most of this processing is going in parallel with the actual RX. And what we are having now with our implementation is that once guest posts the new buffer is sequentially called, it has sequentially to DMA map all the buffers, and when the buffer is processed back and returned from the physical device, we need to sequentially with virtio processing perform the map of DMA buffers. So in the end, we've got to some really hacky measurements. We've added RDTSC in vhost and handle RX, and it appears that copy works faster than what we were trying to achieve. Copy takes about 2 cycles per byte, and with the translation of the descriptors and the DMA map and map takes about 3 and 5 cycles per byte. Now, is it possible to improve what we did or implement Zerocopy RX in some other way? Maybe, we don't know. the first thing that is probably worth trying to is to restore the parallelism between DMA mapping and virtual processing. Maybe it will help and it will allow to save CPU cycles. Another thing that probably would improve the situation is better batching for memory allocations and DMA mapping versus doing it per several packets, per several pages each time. Another thing that maybe allow Zerocopy receive is major redesign to virtual ring. We don't know. And the next is probably the most promising feature is IFXDP-based virtual backend in user space, which sounds like the right way to go. So that's all. Questions? Guys, will you help me with mics, please?
So, did you try disabling the TX mapping? I mean, maybe the TX copy is also bad. It was also better than mapping the TX.
Can you repeat?
I said your findings are that with the RX it was better to copy than to map. What about TX? I mean, so
we didn't actually try, but I believe people who did the TX did the benchmarking back then. TX is quite a long time upstream, so they had their own problems with block of line head of line blocking. But I think performance-wise, I looked back then at the mails, it seemed to improve really.
Have you tried to disable the IMU, to use the IMU PT or disable it completely? Because
no, we didn't.
Probably this is the reason why it was solved, because it's known that IOMU can affect the performance.
We didn't, and probably we won't.
Yeah, I have a question that I didn't quite get why the bottleneck moved to the DMA mapping.
Excuse me?
I mean, the bottleneck moved to the DMA mapping. So
it's not exactly the bottleneck. It's the things that DMA mapping now works in line with virtual processing, rather than it was more in parallel.
In parallel.
So for now, if I run perf, I see that actually DMA mapping takes most of the percentage of the processing. And since it slows things down and increases latency, the throughput also goes down because it's TCP networking, right?
The problem is we didn't. You don't do the DMA mapping in parallel, but sequential. So the frequency is much more than the normal.
It's pretty much the theory we have at that moment, but we didn't investigate it any further. What we've seen with perf is that now the major bottleneck is DMA map and map. Like we were running previously perf on vhost, and we've seen that it spends like 40% of the time in the copy to user. If I'll go back several slides, so here, like 35 of handle RX is spent Intel map page, which may be IOMMU, as somebody said there. But we clearly see that it's the most heavy part of the processing.
Okay, thank you.
Hi. Perhaps as you said that most of the time is taking in the mapping of the DMA, right? So one way to, I think, overcome this and have much better results could be if you enable the hardware GRO. So in that case, the size of the data which you're copying would be much higher. So maybe if the size of it might be just related to the size of the buffer you're trying to copy in. if the size of the buffer is kind of on the smaller side, then basically there would be more mapping and unmapping happening in. So if you have a larger buffer, then maybe the amount of time which is being taken over the mapping and unmapping of a DMA might be slightly less than what actually you could see. You could see much better results than.
That's what we saw when I was talking about batching, like having large chunks and passing them directly to the hardware to make it use larger chunks at once. But we never did it. But we never get to it actually to try.
All right, sure, thanks.
I just wondered, the listify operations, shouldn't this help this? Then you get more packets per thing. So normal network packets are one per, so it runs with one packet per thing. And then with listify, you then just create a list of operations instead, or a list of packets instead, and just pass them all along.
Like putting 2 packets in a page? Or
So no, it does a list of all the packets and then pushes that along. So,
we didn't try.
no, and I know it's in a newer kernel, but I thought maybe that will help us.
You mentioned making massive changes to the weather ring layout on your last slide. Do you already have an idea or suggestions?
Vague idea completely. Just maybe we should do something. No more than that. No, not really.
Okay, thank you.